Hello, Internet. We are live.
Hey everyone, welcome to episode 25 of the Stanford MLSys seminar series. I'm Karan. We have with us, as always, Dan, Piero, Fiodar, and our guest today, Guanhua Wang from UC Berkeley. So this week, we're going to be talking to Guanhua about advances in distributed machine learning training and serving. And as always, there's going to be a 30-minute talk by Guanhua, and then after that, we'll have a 30-minute podcast-style discussion where you can ask questions and post in the live chat. If you want to keep your questions coming in during the talk, feel free to keep posting them in and we'll keep track of them and try to get them across to Guanhua during the podcast style discussion. And a bit about Guanhua. So he's a CS PhD student at UC Berkeley in the RISELab. He's in his final year and he works primarily on ML+Systems. So, perfect alignment with this seminar series. And he works on, fast collective communication for model synchronization, distributed training, and real-time model serving. So hopefully we'll hear a lot more about that today in his talk. Guanhua, you want to take it away?
Yeah, sure. Thanks, Karan, for the intro. Yeah, so hi, everyone. I'm Guanhua Wang. I'm a final year PhD student in the RISELab at UC Berkeley. And today I want to talk about some of my research projects on the distributed machine learning systems. So deep neural networks empower state-of-the-art results across many different applications, such as image classification, speech recognition, robotic control, and also the game playing. To speed up the DNA training and inference, data parallelism and mode parallelism are two widely adopted approaches. In data parallelism, each machine or each GPU holds the full copy of the model, and they train on separate input data. Periodically, they need to do the model synchronization. And in mode parallelism, they share the same input data, but each machine or each GPU only hold a part of the full model. So communication and memory are the main causes for system inefficiency in distributed machine learning. And on the communication side, as I mentioned before, in data parallel training, we need to do the model synchronization periodically, basically after each training iteration. And that can be huge communication overhead. And in model parallel training and inference, we need to transfer a lot of intermediate results, such as the feature maps or the gradients, which is also kind of huge communication overhead. So in order to mitigate the model synchronization overhead in data parallel training, we propose the Blink project, which can provide you the optimal model synchronization scheme given arbitrary network environment. And in order to eliminate the communication in model parallel training and inference, we propose the Sensei project. Basically, it decouples a base model into a bunch of disconnected subnets. Thus, it can eliminate the communication among all those subnets. And on the memory side, as you can see on the left-hand side figure, here we monitor some data parallel training job. On the left-hand side figure, it shows the memory usage. Even though there are at some time period of time, the memory usage reach the on-device memory capacity, but on average, the memory usage is relatively low. And consequently, because a lot of DNA training jobs are memory bounded, so on the right-hand side figure, it shows that the computation cores are consistently underutilized. So in order to increase the memory usage on the device and consequently increase the computation core usage on the device, we propose the Wavelet project. So today I mainly talk about three projects. The first one called Blink, which can provide optimal model synchronization scheme in data parallel training. The second one is called Sensei, which can eliminate the communication in model parallel training and inference. The third one is called Wavelet, which can provide more efficient on-device memory usage. So the first two are on the communication side, and the third one is on the memory side. Let's first dive into the first project called Blink, which is fast and generic collective communication for distributed machine learning. So in order to speed up the DNA training, data parallelism is one of the widely adopted approaches. As you can see on the left-hand side figure, by adopting data parallel training over ImageNet dataset, we can reduce the training time from 150 hours to just 5 hours. And in data parallel training, each GPU may hold the full copy of the model, and periodically they need to do what we call the model synchronization. So what exactly does the model synchronization do? Basically, after each GPU generates its local gradient, here shows as a data W1, 2, 3, 4, model synchronization basically aggregates those gradients together and then broadcasts the aggregated gradient to all the GPUs in use. And that is what we call the model synchronization. And despite there are many performance optimizations, the model synchronization is still a big overhead in data parallel training, especially in the cloud environment. As you can see on the upper figure here, once we scale out to 128 number of GPU for data parallel training, the communication overhead can be up to 50% of the end-to-end DNA training time. And a similar observation has also been found by my colleagues at Microsoft Research. It shows that at the bottom figure, with some language model, the communication overhead can be up to 90% with just a scale out to 16 or 32 GPUs. So to alleviate the communication bottleneck, recently there have been big improvements in both hardware and softwares. So on the hardware side, NVIDIA provides the state-of-the-art hardware like the DGX1 and DGX2 boxes. So what's inside those boxes? Basically, on the computation side, it is embedded with the P100 or V100 GPUs, which can give you 5 to 7 teraflops double precision computation power. And on the communication side, it provides you faster interconnect. For example, they provide the PCIe 3.0, which can give you 10 gigabits per second. And NVIDIA also provides a GPU exclusive link called NVLink, which is a point-to-point communication link only within the GPUs. The first generation with P100 GPU can give you 18 gigabits per second, and the second generation with V100 GPU can give you 23 gigabits per second. Recently, NVIDIA also announced another new hardware called NV Switch, which is basically a fully connected crossbar. And each link on this crossbar can give you 6x NVLink second generation bandwidth, which is equivalent to 130 gigabits per second. On the software side, different companies provide their own collective communication schemes, such as Nico from NVIDIA, Harvard from Uber, and Glue from Facebook. However, all of these collective communication schemes are ring-based collective protocols. So what is a ring-based collective? Here I want to show an example of doing ring-based broadcast in this 4 GPU setting. As you can see on the left-hand side figure, we have 4 GPU 0, 1, 2, 3. They are connected in a kind of ring kind of topology. And here the GPU 0 want to broadcast its 4 chunks of data to GPU 1, 2, and 3. So at the first time slot, the GPU 0 will pass a green chunk, the first chunk, to GPU 1. At the second time slot, the GPU 0 will pass the second chunk, the orange chunk, to GPU 1. At the same time, the GPU 1 will pass the first chunk, the green chunk, to GPU 2, so on and so forth. So after several iterations, this ring-based broadcast finish. And this is what we call ring-based collective communication. So one question we want to ask is, can these hardware and software improvements really alleviate the communication bottleneck in data parallel training? Not really. Here we measure the communication percentage regarding to the end-to-end DNA training time by adopting state-of-the-art hardware like NVLink and software like Nico. Here I want to first show you a 4 GPU setting. Because there are many different 4 GPU allocations within an 8 GPU server, so for each neural net, the communication percentage is not a fixed value, but a range. So as you can see in this 4 GPU setting, the communication overhead can be up to 45% of the end-to-end DNA training time, even by adopting state-of-the-art hardware and softwares. And this high communication percentage is consistent across different number of workers and across different neural nets. So why we still have this high communication overhead even by adopting state-of-the-art hardware and software? It is because the communication overhead becomes more pronounced when we're increasing the GPU computation power. Thus, we need faster collective communication protocols. Next, I will talk about the challenges to achieve faster collective communications. The first challenge is we may have different server configurations. For example, we may have 2 versions of DGX1 box. As shown on the left-hand side figure, if the DGX1 box is embedded with P100 GPU, first here, each link is the first generation, which gives you 18 gigabits per second. And topology-wise, they form a very regular topology, what we call a hypercube. But if the DGX1 box is embedded with V100 GPU, which is shown on the right-hand side figure, first, each link here is the second generation, which can give you 23 gigabits per second. And topology-wise, besides that hypercube topology, here they add another additional ring, which are denoted as those red dashed lines on the right-hand side figure, which makes the topology kind of irregular in this case. So the protocols need to be topology aware in order to effectively use the hardware links. The second challenge is we may have link heterogeneity within an 8 GPU or 16 GPU box. For example, within an 8 GPU DGX server, we may have two kinds of links to connect the GPUs. On the left-hand side, it shows the PCIe links, and on the right-hand side, it shows NVLink topology. Right now, the ring-based collective can only utilize homogeneous links. So why they cannot use heterogeneous links? It is because a low bandwidth PCIe will be the bottleneck if it is included in a high bandwidth NVLink ring. The third challenge is we may have fragmentation issue in multi-tenant clusters. Here we measured 40,000 multi-GPU job at Microsoft. Even though users always require 2 to the power of X number of GPUs, but the real GPU allocation within each GPU server can be weird numbers such as 3, 5, 6, and 7. Some other example of fragmented allocation can be, for example, we have an 8 GPU job across 2 servers. We can allocate 3 GPU on one server and 5 GPU on the other, or 2 GPU on one server and 6 GPU on the other. So why we have this fragmentation issue? It is because many cluster schedulers are not topology aware. And without supporting for efficient job migration, the DN jobs must embrace the fragmentation in order to avoid the queuing delays. And because this fragmentation issue, we may have some irregular topology that does not allow us to form a ring. As you can see on the right-hand side figure, if the GPU placement for a single job use GPU 0, 1, and 4, which denoted as those orange circles, because there are only 2 NVLinks in between, it cannot form a ring. So existing solution will fall back to PCIe if in such a case. So can we do better than the state-of-the-art software given those 3 challenges under the umbrella of the topology heterogeneity? That's the reason we propose the Blink project. So at a high level, how Blink handles topology heterogeneity? Given that we may have different server configurations, the Blink will probe available links at the job runtime. Given that we may have the link heterogeneity issue, Blink can do concurrent data transfer over heterogeneous links. Given that we may have the fragmentation issue in multi-tenant cluster, which has irregular topology that does not allow us to form a ring. In this case, Blink uses spanning trees rather than rings, which can be more flexible and provide optimal performance given arbitrary network environment. Furthermore, we provide NICO-compatible API, which means Blink can be seamlessly integrated with TensorFlow and PyTorch. So here I will show you the Blink workflow. Basically, after the scheduler assigns GPUs to a single job, we probe the available links within those GPUs and pass this information to our Trajan module. So before I talk about the Trajan module, I want to give you an example of why trees are better than rings. Here is a 6 GPU topology, and here we want to do broadcast from GPU 3 on the left to all the other GPUs. So in this case, what NICO does basically is create 2 unidirectional rings. One is in clockwise direction, the other is in a counterclockwise direction. As you can see in this figure, there are several links unused, which are denoted as those red dashed line with a crossbar on top. Actually, in this topology, Blink can pack 3 spanning trees in this topology. And since we have 3 concurrent data transfer channels, which is more than 2 rings, we can do faster data aggregation rather than a ring-based solution. And since we use all the available links in this topology, our performance can be guaranteed to be the optimal. So the Trajan basically try to pack maximum number of spanning trees given any kind of topology. As you can see on the left-hand side figure, if we have 3 GPU fully connected, we can actually pack 3 unidirectional trees, which are shown as the right-hand side figures. We formalize it into an optimization problem with the objective function that maximizes the sum of the bandwidth usage among all the links, with the constraint that the amount of bandwidth usage should not exceed any link's capacity when we pack those spanning trees. And after we solve this problem, we find that we may generate too many trees. For example, we generate 181 spanning trees in an 8 GPU server. Since we have too many trees, the data set per each tree is too small to fully saturate the link bandwidth. Then we make some approximation by adding another constraint, which is shown as a red box in the middle. The new constraint basically says either a tree use all the bandwidth of a link or not use it at all. By doing this integer approximation, we can reduce the tree from 181 to 6 in an 8 GPU server. And after we generate those unidirectional spanning trees, they can be direct support for one-to-many or many-to-one primitives such as reduce or broadcast. We further extend it to many-to-many primitives such as reduce. It's very simple. Basically, we pick a root node in the tree and we reduce towards the root node and then broadcast in the reverse direction. As you can see at the bottom figure, here we pick the GPU4 on the right as a root node. So we do the reduce from left to right and then do the broadcast from right to left. Next, we will pass those spanning trees into our Cogent module. Cogent basically translates the spanning trees into real memory copy or real data transfer commands. So next, we come to the evaluation part. Here we first conduct some macro benchmarks on the DJX1 machines. Here we want to do reduce over 4 GPUs, the GPU 4, 5, 6, which are denoted as those orange circles on the left-hand side figure. And the links in between are denoted as those red arrow lines. And in this case, what Nico does, it basically creates two bidirectional rings. One is using the links across the border, those black arrow lines. The other ring is the link within the middle, those gray dashed lines. As you can see in this figure, there is one link unused between GPU 6 and 7, which is denoted as a red arrow line with a crossbar on top. The reason why in this case Blink can have higher throughput compared with Nico, it is because in this project actually we can pack 3 bidirectional spanning trees. Since we can have 3 concurrent data transfer channels, which is more than 2 rings, we can have higher throughput. And since we use all the valuable links, our solution is guaranteed to be optimal. We measure it across different number of GPUs and across different GPU allocations. And in total, we can achieve broadcasts up to 6x speed up compared with Nico and with 2x DOME. And for reduce, we can achieve up to 8x speed up with 2x DOME. And it translates to end-to-end DNN training time reduction. We can reduce up to 40% of the end-to-end DNN training time. Blink has been filed as a US patent by Microsoft and used inside Microsoft. Blink also gained a lot of attention from industry, such as the PyTorch team at Facebook and the ByteDance company, which is a parent company of the TikTok app. Blink was also featured on news from Baidu and Tencent. The second project is called Sensei, which is we do conv-net decomposition via our class parallelism for fast inference on live data. CNN is a special kind of DNN which enables computers to excel on vision learning tasks, such as image classification, object detection, and semantic segmentation. And recently, we see the trend that both the model set and the input data sets are growing drastically. In order to achieve better model serving accuracy, the model set increased from the original GoogleNet to RISELab to recently a MobileNet. The number of parameters almost increased 200 times. So in order to achieve better model serving accuracy, the model set increased a lot, which leads to that we may have higher latency during the model serving stage. And on the input side, we also see the trend that the image resolution increased a lot from CFAR to ImageNet to COCO. And the larger image resolution also contribute to higher latency during the model serving stage. One point we want to make here is making faster decisions on live data is becoming more and more important. In the case like autonomous driving, for companies like Waymo or Cruise, if the camera captures a frame of image that contain pedestrian, it may save people's life if we can make the stop decision slightly earlier. Recently, giant banks like JP Morgan or Goldman Sachs, they adopt machine learning method for automatic stock trading. And in this case, if one party can make the trading decision slightly faster than the others, it can bring in a huge amount of profits. From a system perspective, making faster decisions on live data meaning making faster decision on each single incoming data item, for example, a single image or a stock's instantaneous price. However, in this case, neither data parallelism nor mode parallelism can reduce live data serving latency, because in data parallelism, we cannot further split an atomic input piece into pieces and do in parallel inference. And in mode parallelism, even though they can share the same input data, but they need to transfer a lot of intermediate results. And usually the time for transfer those intermediate results can be order of magnitude longer than doing single GPU inference on a single image. So can we do better in order to achieve lower latency for the live data inference? And that's the reason we propose the Sensei project. So here is a direct comparison among data parallelism, mode parallelism, and our Sensei's class parallelism. As you can see on the right-hand side figure, basically given a base model, we decouple it into a bunch of binary classifiers. Thus, we can do in parallel inference without communication during the middle. And we only need to aggregate one float value, which is the confidence value indicating whether it's cat or not cat, or dog or not dog. At the very end, basically, we just aggregate one float value at the very end and eliminate the communication during the full forward propagation. So the design of Sensei basically contains 3 steps. The first is called pruning. After we get the fully trained CNN, we pass in the training image belong to a single class into this fully trained CNN and collect the activation statistic in order to conduct our class-specific pruning. After the class-specific pruning, we can pull out a bunch of binary classifiers from the base model. And in the second step, we do something what we call the retraining. Basically, we retrain all the binary classifiers in order to regain some possibly lost test accuracy because of previous pruning stage. And after the retraining, we use all these binary classifiers to do in parallel inference and give you the final decision on the image. So it contains 3 different steps: class-specific pruning, retraining, and combine results back to the original NV predictions. We will just focus on the class-specific pruning here. So in order to pull out the binary classifier, we need to feed in the training image of a single class to a fully trained model and collect activation per neuron. And then we define some activation-based pruning criteria and use our hybrid policy to do the real pruning. Our hybrid policy basically tries to avoid pruning the neurons with activation that first, it has high percentage of near zero values, but at the same time, it also have a few large non-zero values. The second concept I want to introduce here is called grouped classifier. So why we need grouping? It is because 2 reasons. First, we may have too many classes in a data set. For example, in the ImageNet 1K dataset, we have 1,000 classes, and it is unrealistic to pull out 1,000 binary classifier from the base model. And second, we want to achieve arbitrary level of parallelism. For example, on CFR10 dataset, if we only have binary classifier, we can only achieve level of parallelism with number 10. We cannot achieve other level of parallelism numbers such as 2 or 5 with only binary classifiers. So how can we do the grouping automatically to form the grouped classifier? It can be done in 2 steps. First, we collect the feature representation per each training image. Basically, after we pass in all the training images into a fully trained CNN, we collect the feature vector before the last fully connected layer as a feature representation for this particular training image. And then we use t-SNE virtualization to cast this high dimension data into 2 dimensions. As you can see on the right-hand side figure, it shows the t-SNE virtualization on CFR10 dataset. Here, each data point with the same color refers to an image belong to the same class. And after we get this map, we can conduct something like balanced k-mean clustering to do the automatically class grouping. And based on our later analysis over this grouped classifier, we find that by evenly split the original task, we get the grouped classifier with similar model sizes. These similar subnet sizes guarantee that all our grouped classifier can finish the in parallel inference at roughly the same time, which means there is no straggler in between. Then we do the retraining, and after that, we combine the results back to the n-way prediction. Basically, we just here, we add a softmax at the very end. Here, because the cat confidence value is higher than dogs, so we make the final decision as cat. We compare simply with one GPU baseline by conducting one-shot class-specific pruning, and we can achieve inference time reduction by 6x on VGG and 2x on RISELab. So why can we prune so much with just one-shot pruning? It is because we simplify the task. Basically, we simplify the original 10-way prediction task into one-way prediction. Thus, we have more redundancy within the base model. We also compensate with model parallel baseline, and here we can achieve inference time reduction by 18x on VGG and 3x on RISELab. So why there is such a big difference in inference time per image? It is because compared with the model parallel baseline, since it can remove all possible communication and synchronization barriers in the middle. And for ImageNet, we can reduce the inference time per image for 6x on VGG and 3x on RISELab. Next, I'll talk about the synthesis extensions. First, we add a fault tolerance feature on top of synthesis class paradigm. It's very simple. Basically, given that we have a bunch of grouped classifier, here we allow the grouped classifier have some overlapping class coverage, such that each overlapped class, on those each overlapped class, we can do something like a major vote in order to avoid the cases like some machine goes down or there are some malicious machines. And we also extend synthesis to control system in drones. Right now, the control system on drones are centralized. In synthesis, we want to decouple it into a bunch of much smaller control units, where each control unit is only responsible for decision-making of a single propeller. And here are all the team members involved in this project. Last, I will talk about the wavelet project very briefly, which enable efficient DNA training with our TikTok scheduling policy. So all the data parallel and model parallel training jobs are GON scheduled. GON scheduling is the all or nothing scheduling policy, which means it schedules all the in parallel tasks at the same time, or it schedules nothing and wait for the resources to be available to schedule all the in parallel tasks simultaneously. Here we monitor the resource utilization of a GON scheduled task. As shown on left-hand side figure, we monitor data parallel training job using 2 V100 GPU, and we train RISENet on ImageNet dataset. Let's just first look at just one training iteration, which contains a forward and backward propagation, start at time 0.6 and end at time 1.2. So during the forward propagation, the memory usage starts increasing, and at time 0.8 second, the memory usage reaches its peak or its on-device memory capacity. But when you look at the figure at the bottom, which shows the computation core usage, actually the computation core are underutilized in this case. Thus, this computation is memory bounded and leaves around 60% of computation core underutilized. And during the backward propagation, the GPU memory is also underutilized, which is denoted as that red dashed box on the upper figure. Here we call the underutilized memory period as a memory valley period. So the GON scheduling guarantees that all the tasks reach their memory peak and valley time at the same time. Thus, one training task cannot leverage another training task's memory valley period to do more computation. It leaves the memory valley period wasted during the backward propagation. And we also monitor the system utilization on model parallel training, which shows similar results. Even though by adopting job multiplexing schemes such as Gandiva or Celis, it can increase the GPU memory and computation utilization. However, it does not contribute to the training process of a single job. That's the motivation we propose Wavelet project, which can improve system efficiently in single job case. Next, I'll talk about the design. So in data paradigm, we call the GON schedule task as a take wave tasks. And in our TikTok scheduling, actually, by intentionally adding some task launching latency, we can inject another training wave, what we call talk wave tasks, so that the talk wave's forward propagation can happen during the original or the take wave's backward propagation. Thus, it can, by doing this kind of peak memory interleaving, it can achieve near optimal memory usage. And consequently, because we pack 2 waves of training tasks on each GPU, we can also increase the computation core utilization. For model parallel design here, because we have longer memory period during the model parallel training, So instead of inject one talk wave task, here we actually inject 3 talk wave tasks in this 4 GPU setting, which are denoted as blue, green, and orange boxes. And different from pipeline paradigm, where each GPU only hold the single model partition during the whole training session. Here on each GPU, we do the model partition swapping in a round-robin fashion. As you can see on GPU 0, at first time slot, it works on model partition 0. At the second time slot, it works on model partition 1, and then 2, and then 3, so on and so forth. And during the backward propagation, we inject our reduce function to do model synchronization on the same model partition, but across different batches. So for the evaluation on the data parallel training side, we can achieve up to 1.88x speed up over the data parallel training baseline. And for the model parallel training, we can achieve up to 6x speed up over the model parallel training baseline. So the summary of this talk is, in Blink, by packing spanning trees rather than forming rings, we can achieve more flexibility and achieve optimal performance in arbitrary network environment. And in Sensei, by adopting class parallelism, we can eliminate the communication in model parallel training and inference. And in Wavelet, by interleaving the peak memory usage, we can increase the on-device memory usage, and consequently, we can also increase the on-device computation core usage. And that's the end of this talk. Thanks.
Thanks so much, Guanhua. Great talk, and we have a bunch of questions, and I think there's also a question in chat already. And if folks have questions in chat, please feel free to post in the live chat, and we'll try to get those across to Guanhua. So just to kick things off, I guess one thing I was curious to get your thoughts on is there's increasingly been a trend towards like extremely large models, so models that are billions or trillions of parameters even. And so I'm curious if you've thought about what some of the bottlenecks in those settings become, because for example, if you think about something like GPT-3, the model is trained once and it's used like maybe millions of times or billions of times. So I'm curious if you've thought about these types of workloads where some of the effort is shifting towards inference and the models are becoming much larger as well.
Also, for the models like the GPT-3 is very large, and usually we cannot do pre-training by our own. So in this case, actually for the inference task, I think we can adopt something like our Sensei approach. And right now we are working on that. Basically, we want to work on what we call Sensei NLP. And we try to decouple that huge model into a bunch of disconnect subnets. Basically, we decouple it based on the vocabulary. For example, some of the vocabulary or words are related to theater or movies. We try to decouple such a small subnet. And some other vocabulary may relate to sports, like soccer. Yeah, we try to decouple another subnet for sports, something like that.
I see. And this, typically, is this, do you think, a general strategy that people should look into more, this idea of decomposing into subnetworks and then using that to speed up?
I guess so, because based on my experience, a lot of in-parallel inference tasks are like the communication bounded. You need to transfer the intermediate results. Yeah.
Thanks.
Sure.
I think I have like a question that is kind of related to this, which is regarding the SenseAI work, which is like a really great idea to do this separation per class in CNN models. I think it's a really nice idea. My question is, actually, each submodel, because you do both the pruning and retraining,
yes,
they're not exactly the same as the original model, right?
No.
So is there performance in terms of like accuracy, like drop or anything like that? Or what was your experience with that?
Oh, we need to guarantee, when we do the pruning, we need to guarantee that our test accuracy won't drop. Yeah. We have this like our bottom line. We never make the accuracy drop. Yeah.
I see. But is there like something specific that you do to avoid that, drop in accuracy? Or
no, if we prune too much accuracy drop, we just abandon this scheme. Yeah.
So basically, you have like a boundary that says
yes,
keep on pruning until unless the performance drops below a certain amount or something like that.
Right.
Got it. That's very interesting. And what about the retraining part? I'm also curious because this pruning and retraining, to me, it reminds me a little bit about the lottery ticket hypothesis, where you that, or is what completely
Oh,
different?
well, actually, for the retraining, because I don't have a lot of time to talk, for retraining, two things are really important. First is we need to balance the positive and negative samples during each training iteration. And second, we also need to change the loss function accordingly. Of course, if we want to pull out the binary classifier, we need to change the loss function into binary cross entropy loss. And
Yeah.
if we want to,
Yeah, that makes a lot of sense because otherwise you will have a lot of negatives, right?
yeah,
So
yeah.
makes a lot of sense. One last question on this topic is,
Uh-huh.
do you think that this could be generalized to other architectures, other models, other tasks easily?
Yes, right now we work on LSTM, we work on BERT, and we are working on some reinforcement learning models. I
Yeah.
think it's quite general. Yeah.
Yeah. Amazing. Thank you very much for your answer.
Thanks.
Guanhua, so kind of jumping off of Piero's last question, one of the great, I think, mysteries about deep learning is that the models are, surprisingly generalizable in a lot of different settings. I wonder, have you done any studies about that? Like after you do the pruning, obviously there's a lot fewer weights. In some sense, less model capacity. Do you notice, have you done any studies like, are they more or less robust to things like image corruptions or for use kind of like out of distribution? Have you looked into any of those questions or those properties?
Yeah, I think it's less robust, of course, because we have like lower capacity within each subnet. Yeah, so that's the reason we propose that a robust sensing or a robust class paradigm thing. Yeah, we try to add redundancy. Yeah.
Yeah, nice. I guess jumping over to the first bit of work that you talked about, the Blink work. One of the things that always interests me about kind of performance work in terms of like throughput and latency is I always wonder, how do the communication bottlenecks and the system design change when you scale up your compute by 10x or 100x? So I think you're largely talking about kind of like single rack machines like DGX1, DGX2, things like that. Do you have any thoughts or insights about how does your system design, how do the major challenges change if you scale up to data center size compute or even like distributed GPUs across the cloud? How do you change the communication protocols to adapt to this? Do you have a good sense of like what the the communication bottlenecks will be in settings like that?
Yeah, sure. Yeah, so I think right now there are two trends. The first trend is like from Google. Within those TPUs, they have some very powerful interconnects. Basically, they have a full mesh, which means all the TPU are fully connected. And in this case, our Blink approach can be directly adopted to that fully connected networks. And another trend is from NVIDIA. Basically, as you can see the trend that recently NVIDIA just tried to group more and more GPU inside a single box. And in that case, our Blink can also be applied to those DGX2 or even DGX3 box in the future, maybe contains 100 or 1,000 GPU within a box. Yeah.
Cool. While we're talking about Blink, I think Travis Adair had a couple questions in the chat, and of course, Travis was our guest a couple weeks ago, or months at this point. So Travis is wondering, can Blink be used as a drop-in replacement for NCCL? Have you benchmarked performance with recent versions of NCCL that support non-ring topologies? And I'll also ask, because I think it's always nice when you get this question, if Blink can be used as a drop-in replacement, where can Travis go download it?
Yeah, so I think because of the patent issue, right now it's only used inside Microsoft. And we are previously we only compare with the older version, the Nico 2.6, if I remember correctly. And later on, because I also talked to folks from the Nico team at NVIDIA, they also adopted this kind of tree-based solution into their Nico library. I think right now, the performance should be matched between Blink and Nico because they also have those spanning trees. Yeah.
Cool. Thanks so much.
Yeah, I guess just as a follow-up, I think Morley had a question about, and I think this is an interesting kind of line of thinking, which is you talked a little bit about the relationship between topology and these interconnects, and we also touched on how Google with their QPU pods is doing something a little bit different. So I wonder, like, do you have any thoughts on, code design? I think this is what Murli's question is also about, like between these emerging kind of AI accelerators and how people are actually designing the hardware that's going to run these workloads. Do you think that there are ways in which, people can design these a lot better and utilize, more efficiently the memory and the compute for like training and inference workloads?
Yeah, I think NVIDIA actually did a good job. Right now, they can have the high bandwidth, the NV switch, which is over 100 gigabytes per second, basically at the same level of reading the GPU local memory. So right now, the NVIDIA V100 GPU, the local memory I/O can be around 500 to 600 gigabytes per second, and their NV switch can give you like 130 or 150 gigabytes per second. I think maybe after several years, if they can make the wider NV link, they can try to like eliminate this communication bottleneck. You read remote memory just as you read your local memory with the same speed, I guess. Yeah.
And in terms of just like new kind of hardware, have you thought about extending Blink and some of these other techniques that you've talked about into kind of new hardware chips that might be coming out? I know you talked a little bit about Microsoft using some of your work, and I'm curious what kind of things you learned from that collaboration and some of the lessons there.
Yeah, so right now in Microsoft, I learned what lesson from there is basically there are a lot of engineering work once you want to deploy your research project into industry. For example, we spend a lot of time just to find a bug that we need to throw some exception if there is one port on the switch it goes down. Yeah, because that takes us around 2 months to just fix that issue, because we never think about there are some hardware failure within the switch. Yeah, and for the Wavelet project right now, I will plan to try to collaborate with Tianqi at SMU and also some AWS folks, because we overlap the forward propagation with another backward propagation. Those computation kernels are different. And right now we directly overlap those, they will try to block each other basically during the computation stage. And we want to merge on the forward and backward propagation kernel into a single kernel such that they won't block each other. Yeah.
Awesome. I think Fiodar had a question.
Yeah, I wanted to kind of come back to SenseAI because it's a really cool kind of idea.
Yeah.
And I was thinking about one of the motivating applications you gave, which was autonomous vehicles.
Yes.
In an autonomous vehicle, you want to be detecting a lot of different things. But perhaps not all of them are at the same level of priority. So probably, pedestrians and cars are priority class, like number one. You definitely want to get those. So it makes sense to then, maybe decompose your model or prune it rather, like you did in SenseAI, and then like run those detectors right away. But I was curious, in general, how would you go about like scheduling those different parts of the pruned models to run inference? Say you actually want to be able to detect like a bunch of different classes, but perhaps at different levels of priority. So you get the really low latency for your most important parts, and then perhaps higher latency for the less important classes. Have you thought about that at all?
No, but right now I talk with some people work on autonomous driving. Basically, they want to use something as a side channel. They have their main channel to do the original version of perception. But as second channel using Sensei, basically we want to detect those dangerous signals, such as a pedestrian or something like that. And they also try to, for example, we decouple a base model into a bunch of binary classifiers. They also try to set some binary classifier with higher priority and only use those binary classifiers rather than use all the binary classifiers we have.
Yeah. Got it. That makes a lot of sense.
Yeah. Because they are
Cool.
all independent. Yeah.
Hey, Guanhua, we had a question from the audience from Sanjeev Kumar that I'll try to paraphrase a little bit. So you're the title of your talk is kind of disruptive distributed ML research. And my question is, as you kind of introduce these new abstractions and new ways of, parallelizing models, of kind of interleaving, forward passes and backward passes through wavelet, decomposing models like through Sensei, how should people think about kind of capacity planning, and how do these techniques kind of change the calculus of what people think is possible, what people think that they can really do kind of with modern hardware, and in modern systems?
Yeah, for example, for the Sensei modern hardware, like we try to collaborate with a drone company in China called DJI. Yeah, right now they are, as I mentioned before, they are using a centralized control system. But actually, within each propeller of the drone, they also have a very low power chip that can do some kind of sensor data pre-processing, etc. And what we're trying to do is trying to insert our smaller control unit within those low power chips inside the propeller. That's one hardware that we try to collaborate on. Yeah, right now.
Yeah. Kind of, speaking about, machine learning models running in propellers, kind of makes me think about, situations with kind of on the edge with kind of extreme resource constraints.
Yes.
I wonder if you've done any work there, like, could we be running models on my GoPro next week or anytime soon? How do those things kind of change the calculus?
Yeah, I think it is doable because usually the reinforcement learning model are actually much smaller compared with like the language model or the CNNs. And we further decouple it or further shrink down the model size such that the smaller unit can really be deployed on very low power chips, like the propeller or the GoPro thing. Yeah.
Cool.
It
Thank
is
you.
doable, yeah. Thanks.
Guanhua, so I wanted to ask you, you talked a little bit about your TikTok scheduling work, and I'm curious, like, how you think about identifying, new bottlenecks in some of these, pipelines, and what is the kind of process that people should think through when they're trying to find bottlenecks in their workflows, as far as, let's say training goes, right? So you talked about, like, at least in the question Q&A, you talked a little bit about trying to fuse kernels and stuff like that for or backward passes as sort of ongoing or future work. But I'm curious, like, how should people, how do you think people should like go about, finding these inefficiencies in their workflows, and what kind of diagnostic tools do you think are most helpful there?
So I mainly work on GPU, so the diagnostic tool I use is the NVIDIA virtualization tool. Yeah, basically, yeah, they can provide you very detailed fine-grained analysis over those kernels or some memory copies. Yeah.
So do you think it's still kind of a thing which only an expert can do and not necessarily anyone?
Actually, I think you can take a look at the recent NVIDIA virtualization tool. It's not some expert only tool. It is very user friendly, actually. Yeah. Okay. The only thing is it only works in Windows machine. Yeah.
It seems like a small but important bottleneck for all those Linux users.
Yeah, because previously when we're doing the analysis, we need to switch all the metadata into a Windows machine, and after do the analysis, we need to send it back to the Linux machine.
Okay, this is a classic grad school story. It sounds like doing workarounds.
Well, actually, you presented basically 3 different works that address 3 different aspects.
Right.
Model parallelism, data parallelism, and bottlenecks in the memory usage. I'm curious, like, what are assuming that these are solved, right, or better solved than they were before. I'm curious, what are other bottlenecks that you think are there in modern machine learning pipelines that we should look at and address and improve?
Another big bottleneck, I guess, is on the data layout. For example, you have a high dimensional data. should you like expand it in the first dimension first or the second dimension first? For example, in the convolution, it has a height, width, number of channels, number of layers, stuff like 4-dimensional kernel. It's 4-dimensional tensor. How can you do the data layout? It's a very big challenge. And actually, there are a lot of people working on that direction right now.
Oh, that's very interesting. Actually, last week we had Karan who gave a talk to this series, and I'm curious of your take of one of the points that she highlighted particularly, which is architectures which have submodules that have different performance profiles. Like, for instance, there's an embedding layer that is really heavy on memory and low on compute, and maybe there's another layer which is a convolutional or transformer layer which is high on compute and maybe less heavy on memory. Do you think that that's like an interesting also thing to explore?
From my perspective, I think it's not very general. It's basically model dependent.
I see.
Yeah.
So you don't care about the modeling part specifically. You want to be more.
For me, maybe not.
Understand. Yeah. Thank you for your answer.
Guanhua, your point about data layouts was really interesting and got me thinking about recently there's been a lot of work that's been becoming popular about kind of ripping convnets out of vision as much as we can. So there are vision transformers. Recently there's these MLP mixers that just try to create a model just full of MLPs in various different ways. I wonder, from your perspective, how do the kind of performance considerations change, either becoming like more complicated because you never know what you'll get, or maybe potentially getting simpler because everything is just a transformer now, or everything is just an MLP. Have you thought at all about how those performance, everything from data layout to how you split up a model and everything like that, how do those things change as we kind of potentially commoditize the architectures across different modalities?
Yeah, I think it mainly depends on the machine learning research trend, because previously we always believed that the transformers are better than convolutions in language processing. But the recent paper from Goel, they said convolution actually works better than transformers. I'm not a machine learning expert, but if that's the case, convolution are better than transformer. Right now, NVIDIA provides cuBLAS, which is very efficient implementation for the convolution computation. I think you can directly use that. Yeah.
Right. It's really interesting. For the longest time, we've thought that, inductive biases are super important as we design new architectures and new models. I wonder what the world looks like when, if it's possible that, everything is the same model modulo some like small changes. What do you think that means for kind of, hardware, software co-design, hardware model co-design? Like you mentioned, convolutions are, NVIDIA has optimized for convolutions quite a bit. Do you think there will be similar things for optimizing for, attention or tons of MLPs or things like that?
Yeah. So it just depends on whether it's hot or not. It become more and more popular. I think NVIDIA will provide another library just for NLP, just for transformer or RNN-based model. Yeah.
Cool. I guess as we kind of start coming to the end of the hour, I was wondering, what's kind of next on the plate for you? What are you thinking about working on? How are you going to like extend these works? What are the interesting questions that you're still wanting to ask going forward?
For me, I think the next step I will take is trying to figure out some ways that whether we can pre-train the language model in academia. Yeah, basically, I want to use some other new hardware, like some ASICs chips or FPGAs, to see whether there is some possibility for us to train the BERT, to do the pre-training or pre-training of BERT or GPT-3 by our own. Because for FPGAs, they have larger memory compared with GPU. But the hard or the challenge is that the FPGAs memory I/O actually has much lower bandwidth compared with GPU. They only can give you like 10 or 20 gigabytes per second, versus GPU can give you 500 or 600. Yeah.
Gotcha.
So are
Yeah,
you,
that sounds super cool. You know, certainly. I know a few people who'd want to use such a thing if you could figure it out.
Okay. Yeah, I will try my best.
no, yeah, I was curious if you were thinking of something like a, learning from home type of situation where, you can have people contribute hardware in order to train a large language model, something like that, maybe. That's on the
Yeah.
card.
Yeah, because I think at least a large group at the CMU, they are trying to deploy machine learning in some new hardware. Yeah. And maybe they also do some coding on the hardware itself.
I see. Well, Guanhua, since we're very close to 2 o'clock, I want to really thank you for sharing your work with us and the audience and really interesting kind of and as your talk title said, disruptive work. So thanks so much for joining, and I also want to thank everybody in the audience for tuning in this week. Yeah, if you've not already subscribed to the YouTube channel, please press subscribe and try to get us to 5K subscribers. And you can also go to our website, mlsys.stanford.edu, to check out the speaker schedule and to subscribe to our mailing list. And I think next week, who do we have, Dan? I always put Dan on the spot.
We have Tim.
Sorry?
Next week we've got Tim Kraska from MIT. He's going to be talking about I think it was instance-aware data systems or optimizing instance-specific data systems. Yeah.
I think mainly on like how to use machine learning method to do more efficient scheduling on databases. Yeah.
Right. Yeah.
Yeah, because we talked last week.
Okay. Yeah, there's everybody's connected in the MLSys community. So yeah, thank you so much for joining, and see you next week. Thanks. Bye.